Okay, yeah. And so, right, so the number of hydrogens determines the number of signals. And Caitlin, the n plus one, that's also referring to the multiplicity. So the number of neighboring hydrogens plus one is what determines the splitting or the multiplicity. But just how many signals there are themselves, that's just determined by how many different hydrogens there are in the molecule. So we've determined, or we've talked about the number of signals. That's the number of hydrogens. You guys have already told me about the splitting now. So the splitting or multiplicity is determined by the number of hydrogens on neighboring carbon atoms. And then as Caitlin said, the splitting is the number of neighboring hydrogens plus one. All right, so we've got the number of signals, the multiplicity of those signals. What determines the chemical shift? So that's where it is on the x-axis. And if it's further to the left on the x-axis, then we say that it's shifted further. It has a greater chemical shift. So there are certain things that if the hydrogens are near these things, it causes them to shift. So what are the two things that'll cause the chemical shift to move downfield or be shifted downfield?
The
The
oxygen.
oxygen. Yeah, oxygen.
Yeah,
Yeah.
or and so oxygen is definitely part of it, and it's but more generally electronegative atoms. So oxygen being electronegative is definitely one of them, and it shows up in the examples we give a lot. So yeah, so oxygen, other electronegative atoms would do it too. So chlorines, fluorines, nitrogens, right. So that's one, and then what's the other thing that it can that the hydrogens, if they're close to it, will cause a greater chemical shift? Yep, that's right. Pi bonds, exactly. So they could be triple bonds too, but Caitlin's right. Double bonds, triple bonds, pi bonds will cause a greater chemical shift. So, and the closer the hydrogens are to the pi bonds or the electronegative atoms, the greater the chemical shift. Good. And then what about the one we haven't talked about yet, integration? So what determines the integration of a signal?
Rational structure now.
Nope, nope. So not the resonance structure. Yeah, so Nahom, right. It's the number of hydrogen atoms that are contributing to that signal, right? So the multiplicity is determined by the number of neighboring hydrogens. The integration is determined by the number of hydrogens that are making that signal. All right, so we want to make a prediction about these four things for the molecules in this example that I have. So are you guys seeing the PowerPoint? So like I've got a molecule with an ester and an ether in it on the top left. Are you guys seeing that? Okay, thank you. All right. And so I'm going to go back to that. And just to let you know, I can't see my PowerPoint and the Zoom at the same time. So I'm getting ready to look at the PowerPoint, so I'm not going to see the chat. Um, so we want to make a prediction on the number of signals, the integration, and the multiplicity for each of these molecules. And I left out the chemical shift. That's a little bit harder to predict. Although on some of these, I may ask an additional question about having you tell me which signal would have the greatest chemical shift. So let's focus on the one on the top left for right now. And if you want, you can, this is posted on D2L, as are the keys. So you can be checking your answers if you don't want to wait for me as well. But for the one on the top left, how many signals would we expect there to be in the proton NMR for that molecule?
4.
Yeah, I like 4 signals as well. So we're going to have, our signals are going to be, that would be 1. Let's see, let me do different colors. Maybe, but I don't know how. Let me try it this way. Yeah, here we go. So that would be 1. Oh, try that. Okay. Here we go. All right. Two. I've got one hydrogen here. That would be three. And then these two methyl groups are identical. So the two that I circled in orange, since those hydrogens are the same, they would contribute to the same signal. So we would have four signals in that case.
Dr. Shepard, sorry. Can you repeat one more time what is the name of the document?
Oh, if you look on D2L, it should if you go into the lab materials and lab week 1, this is the NMR examples.
Got it. Thank you.
Okay, so let's focus on the one that I've circled here with the black ink. So what would be the integration value for that signal?
Three.
Yeah, and I think if I heard that correctly, I think I heard 3.
It will be tertiary.
Yeah, or you're right. So you're definitely on the right idea. So tertiary is right. We wouldn't usually use that term in this case. We would just give the number. We would say the integration is 3. But your idea is correct. And then what about and that's because there's 3 hydrogens on that black carbon that I circled. So what about, well, I can't be as clever as I want. So what about the blue signal? What would the integration be there?
2.
Yep. And then the pink?
1.
Yep, there's 1 hydrogen there. And how about the orange?
6.
Yep. And so we add up all the hydrogens that contribute the same signal. We would add them together. And so those would be the integration values. And then if we went back to the things have just gone very wrong. All right, well, we'll go with this. So for sorry. I know you guys didn't plan on logging in to watch me fumble with the Zoom all time. Why? So what would be the multiplicity of the black signal?
It'd be a singlet.
Exactly right. Since there's only the one neighboring carbon and it doesn't have any hydrogens, 0 plus 1 would be 1. And so we'd call that a singlet. What about the multiplicity for the blue signal?
Singlet still. Singlet also.
Yes, exactly right. To the left, there's the oxygen. To the right, there's the oxygen. And they don't have any hydrogens. So we'd predict that it would be a singlet. But even if there were hydrogens that are attached to oxygens typically don't contribute to the splitting or the multiplicity. So, right, that would be also a singlet. All right, now the pink ones may be more interesting. What would be the multiplicity in that case?
It'd be a septet, like 7.
Yeah, exactly right. So we add up all of the neighboring hydrogens, assuming that they were identical, and then do the plus 1. So there's 1, 2, 3, 4, 5, 6. So 6 plus 1, that would be a septet. And then how about the orange signal? I'm sorry, I'm mixing temperature. Let's use the right one. Multiplicity.
Singlet.
Okay.
Oh,
Yeah,
the doublet there.
right. I think for the orange, it would be a doublet. So when you're determining the multiplicity of the orange signal, when we did the pink, we had to add the oranges together. But to determine the orange, just pick one of them. So I'm gonna use this one. And so there's only one neighboring carbon. It has one hydrogen. So that's going to make it 1 + 1. The orange multiplicity is going to be a double. All right. Any questions on this first example? All right. Let's do one more of these. I don't want to go through them all because that might get to be a little bit painful for you. But any ones that we don't do, if this is something that you find helpful, I'd be happy when I'm done doing the examples to look at more with you, or if you want to look at them out on your own. The answers are on D2L, so you can check them there, and then if we're getting different uh, results, I'd be happy to talk about that for sure. Let me see. Erase all that. Okay, let's jump down to yeah, I kind of like this middle one on the left. Let's take a look at this one. So how many signals would you expect in this case?
Four.
5.
Oh, five, right.
I think I liked home. I think you might have said 4 initially. I think I like that one better, right? So let me count them and
Oh,
see.
4, yes, it's 4.
Right, so those two methyls are identical, so that would be 1. But now this carbon here doesn't have any hydrogens, so that one's out. But that carbon has hydrogens. None of the other carbons that have hydrogens are going to be identical. And so I think we're going to end up with 4 signals. Let's use pink again. All right, so for this, for this green one, what would the integration be?
Two.
Yep, it would be 2. And then the pink, I'm gonna go. I'm just gonna say some of these answers with the virtual. The red integration, there's 2 hydrogens there. That's also going to be 2. And then for the orange,
6.
it's going to be 6. All right. Now, if you were going to, if I asked this on a quiz or a test, if this is what you put for the answer, I'd be okay with that. But I think there's maybe a better answer. And if we were to run this exact molecule in an NMR spectrometer, this is not exactly the results that the computer is going to spit out. What would be different about it? Or what's another way that might be more correct for the integration values and that would match what the program would tell us the integration values are if it didn't know what the compound is?
They all have a common factor, so you could have them all.
Yeah, exactly right. The good, Colin. The integration values formally don't actually tell us the number of hydrogens. They tell us the relative number of hydrogens. So in this case, if all the hydrogens are divisible by a common factor, in this case 2, then they would all be reduced. So if you were given this spectrum, the integration values you would be given wouldn't be 2, 2, 2, 6. Since those are all divisible by 2, the actual relative values would be 1, 1, 1, and 3. And so let me give you guys a chance. Does that make sense, or do you remember that, or does that need more explanation?
I think that I remember.
Okay, thanks, Caitlin. Um, okay, so then let's look at the multiplicities as well. Right, and so then again, the green one is here. And so what would I won't ask you to do all of them again. I'll start just giving the answers, but if you guys would give me this green one, what would be the multiplicity of that signal?
That will be single, no, or double.
I'm seeing in the chat on my iPad, it's popping up as things so I can see them. So I'm seeing triplets, and I like triplets. So there's the neighboring oxygen. It doesn't have any hydrogens, and even if it did, they wouldn't split anyway because they'd have been on an oxygen. But then down here, I have 2 hydrogens. So then for the multiplicity, it's the neighboring hydrogens 2 plus 1. So that would be triplet, right? And then the pink one, and so the pink one is here. It has a neighboring carbon, but that carbon doesn't have any hydrogens. And then it has this neighboring carbon with 2, so 2 plus 1. That's going to be a triplet again. And then the red one, which is the one up here, there's a carbon, but no hydrogens. There's a carbon, but no hydrogens. So 0 plus 1, that's going to be a singlet. And then for the orange, we only have to consider one of them. Don't consider them together. So if I was to take this one, it has the one neighboring carbon, but there are no hydrogens on it. So that's going to be a singlet again. All right. So I thought this one had a couple features that I wanted to be sure to point out. And I was wrong. It doesn't have the features I want to point out. So I'm not going to do another complete example, but there are a couple that I wanted to pick out just because they had some interesting wrinkles that we've talked about that would be good to remind us. So let me go, if I can make my computer do it. Oh, right. This. There we go. Okay. So if I look at this one on the right-hand side, I don't want to do the whole thing, but what I would like you to do is I would like you to tell me this one that I just circled, what would the splitting of that signal be?
Some sort of multiplet.
Yeah, exactly right. So the reason we said multiplet as opposed to giving an actual number is because there are 2 different types of neighboring hydrogens, right? We've got the ones here that I'm going to put the square around, and then we've got the one here that I'm going to put a triangle on, right? And obviously my square hydrogens and my triangle hydrogens are not identical. And so anytime a proton NMR signal is being split by 2 different types of hydrogens, the splitting is often complicated. And so sometimes it just looks like a blob, like there's just a whole bunch of splitting. And that's what we would call a multiplet. Um, now, I think it is important to point out sometimes, and it's kind of by accident, it's like we get a bunch of cancellation of errors, but sometimes it'll actually come out and it really will be n+1. So sometimes, and it depends on the exact molecule, it can also depend on the spectrometer that we're using. Sometimes if we took this spectrum, that signal would show up as a multiplet or just be a bunch of peaks without, there should be a bunch of them without a way to make sense necessarily of how many there are. But at other times, maybe in this molecule, maybe in other molecules, or maybe if we used a different spectrometer, we would get it. Sometimes we do get the n+1 number. So it might show up as there's 2 hydrogens on the square, there's 3 on the triangles, so that's 5 total. It is possible that the circle NMR signal will show up as a sextet, as a 5+1. We just don't know. And so you want to kind of be on the lookout for both, because maybe it would be a multiplet, maybe it would actually come out as a clean sextet. It's hard to predict just looking at the molecule and not knowing what spectrometer I'm using. Okay, so that can sometimes be a little bit tricky. So let me pause for a second and see if anybody has questions on that particular idea. Okay, well then let me clear my drawings. Let's just do one more of these. And again, not the whole thing, just one question I want to ask. Yeah, if you'll tell me the bottom left one, so the one I'm kind of circling now, how many signals would we expect in the NMR, proton NMR of this compound?
Three.
Yeah, Edwin, that's really good. There would be 3, right? Because this molecule has a lot of symmetry, there's essentially a reflection plane going right down the middle of the molecule. And so what that means is these one on the ends are identical. So that would be 1 signal. And then let me use a different color and a different shape. These ones next to it that I'm making circles in pink, that would be a second signal, and they would be identical. And then we'd also have this one in the middle. I'll make that one red and a triangle. And so those would be the 3 signals we would get in the NMR for that compound. Good. Okay, so what I'd like to do next for spectroscopy is I have several of the spectroscopy combo examples, and I'd like to do at least one of those together. So I'm going to stop sharing this, and I'm going to share. Let me open it first. Yeah, this is I think a good one to work on together. So this is going to be, so I'm going to share my document, but if you want to pull it up separately in the same folder that NMR document was, I'm going to get ready to look at spectroscopy example 1. Maybe. All right. So in this case, I've put the elemental analysis, but for the when we have the spectroscopy examples on the on the tests in this course, I'm not going to have you do the elemental analysis. So in this case, I just gave you the empirical formula, so we can save a little bit of time. We don't have to use the mass percentages to get the empirical formula. That was just given to us. So then. I often like, once I know the empirical formula, the next thing that I like to do is determine the molecular formula. So if I have the empirical formula, and then based on the other data I'm getting, how do I determine the molecular formula?
If the grams per moles add up.
Yeah, and I know what you mean, Edwin. What are you going to compare that to? So if we add up the molar mass of the empirical formula, what do I compare that to specifically?
To your mass spectra, it'd be the 126 or 136.
Yeah, 136, exactly. Yeah, exactly right. So that's good, right? So the parent ion peak, the peak that's the furthest to the right in our mass spectrum, gives us the molar mass of the compound. And so if we add up the molar mass of our empirical formula and it matches the molar mass from the mass spectrum, then I know that the empirical formula is the molecular formula. And that happens not infrequently. But what could also happen is the molar mass of the empirical formula comes out to be smaller than from the mass spectrum. And when that's the case, that just means the molecular formula is bigger than the empirical formula. And so I have to multiply the empirical formula by some constant to get the molecular formula. And that's going to be an integer. It's going to be 2, 3, 4, whatever. So the first thing the molecular formula is more useful to us because that tells us the actual number of atoms rather than the relative number of atoms that the empirical formula does. So for the C9H12O, I'll do 9 times 12 plus 12 for the hydrogens plus 16 for the oxygen. I get 136, which matches the molar mass from the mass spectrum. And so that tells me that this is also the molecular formula. Okay. And so there's not necessarily a right answer. But once I have the molecular formula, I always do one thing next that I can get just from the molecular formula. So what's something useful that I can determine out this compound just from the molecular formula? Oh, Caitlin already posted it. She beat me to it, right? We want to do the HDI. So once I get the molecular formula, I always calculate the HDI next. And so for the HDI, that's 2 times the number of carbons plus 2. So 2 times 9 is 18, plus 2 is 20. And then if I had any nitrogens, I would add that to that number, but I don't have any nitrogens. And then I ignore the number of oxygens. That doesn't impact the HDI. And then, so I do 2 times carbon plus 2. I do the nitrogens if I have to. And then I would subtract the number of hydrogens and halogens from that. We don't have any halogens. I only have hydrogens. So 2 times 9 is 18 plus 2 is 20. Subtract the hydrogens. 20 minus 12, I get 8. And then divide that number by 2, and that gives us the HDI. So I already see it in the chat. In this case, our HDI is 4. And then, good, Caitlin, if our HDI is 4 bigger, I call that the benzene rule. That almost certainly means, based on the smaller molecules that we tend to do in these examples, that means we've got a benzene ring. That's just about the only way to get such a high HDI with a relatively small molecule. And so I know I've got a benzene. And could I have, even without looking at anything else, if I know the HDI is 4, and so that means I have a benzene, could I have a carbon-oxygen double bond in this molecule? Okay, so let me ask that a different way. If a molecule, so not this molecule necessarily, but just any generic molecule, if it has one C double bond O and no other double bonds or rings, what would its HDI be? So the HDI is the number of pi bonds or rings. So if I have just one C double bond O and no other rings or double bonds, that would be one pi bond and no rings. So every double bond that we have gives us or adds 1 to the HDI. But benzene uses up all 4 of our degrees of unsaturation. So that tells me, other than the benzene, there can't be any other pi bonds or rings. So I immediately know I can't have any carboxylic acids or um, esters or ketones or aldehydes because that would make my HDI too big. The benzene is going to use all four of my HDI. So I always like to, when I'm trying to come up with my formulas, I sort of keep track of my formula, right? And every time I figure out what one of my functional groups are, right, that uses up some of my atoms. And so once I kind of figure out what all my pieces are, then it makes it easier to put together. And so then in addition to getting my formula of what I draw to match the formula I'm given, I'm also thinking about the degrees of unsaturation. I'm thinking, okay, have I accounted for all my degrees of unsaturation? And once I do, then I know, okay, I can't make any more rings or pi bonds. So when I see my HDI is exactly 4, I know I've got a benzene ring, but then that's it for rings and pi bonds. All right. So now, is there anything else besides the molar mass that we can determine from the mass spectrum?
Loss of fragments or
Exactly
popular
right.
fragments.
There's the loss of common fragments. And so to get that, we're going to take the difference between the mass of the parent ion peak and all the other peaks. And I'm not going to try and display the table now because I'm already displaying the sheet. But I'll give you that same table that you would have had in Orgo 1, those data packets that have the table of the common mass spectrum fragments. And then for most of the examples that I give, and then certainly on anything that I give on a test, because if they're not labeled, it can be kind of hard to tell exactly what the X value of the different peaks are. I'll typically put, if there's a peak I want you to check, I'll put the numerical value of the mass to charge ratio or the x-axis value on top of the peak so it's easier to see what they are. So in this case, if I only gave you this one, that's really the only one I'm kind of asking you to check. And so 136 minus 121 is 15. It's okay if you don't remember. You'll have the table that has all these values. But does anybody remember, is 15 one of our common fragments?
Yes.
Mhm. It is, yep, and that's a methyl. So the 136 minus 121 giving us 15, that's most likely due to a loss of a methyl group. So I know my original molecule probably has a methyl. Although you probably remember last semester from some of the examples, we want to think of the common fragments in the mass spectrum as being more suggestions, right? It might have lost a methyl, but it might have just lost enough combination of other things that added up to 15. All right. So I'm going to erase what I've written just so I can. Here we go. Scroll down a little bit. Okay. So in the IR, one of the first things I typically will do is draw a line. Let's use a different color. Looks like it won't let me do it on the iPad. So let me try and draw it here. My laptop. All right, so a line at 1500. It's kind of straight. And a line at 3000. Okay, that's going very poorly. All right, that line is terrible. But I'll tell you, right, this little thing right here, that is above 3000, right? And then this mess is below 3000. All right, so my next question, and I figured out how to see my chat and the thing I'm sharing at the same time. So if you want to throw stuff in the chat, feel free. I figured out how to see those now. So what patterns do we see in the diagnostic? Can we identify in the diagnostic region of the IR?
Double carbon bonds.
Yeah, exactly. So they're relatively narrow, and so these are like carbon-carbon double bonds. Now, Caton, I'm glad you put in the C double bond O in the chat. Those could have been, right? They're kind of intense. And so they might have been carbon-oxygen double bonds. But I know from the HDI that benzene is going to use up all my degrees of unsaturation. And so the carbon-carbon double bonds that we're seeing, those are part of the benzene ring. But in this case, I know it can't be C double bond O because I've used up all my HDIs with the benzene. And if I'd had C double bond O's, that would have made my HDI higher. So I know in this case that it's just carbon-carbon double bonds, no carbon-oxygen double bonds. Okay, but I can also see in the chat the OH, and that's absolutely right. At around 3,400 wave numbers, if you have a really intense, broad signal like we do here, that is sort of a classic signal of an alcohol, the OH stretch in an alcohol. And then these other two that I circled. So these here that are a little bit more intense, that are below 3,000 wave numbers, those are CH stretches. And if they're less than 3,000 wave numbers, exactly right, Caitlin, that's going to be my sp3 hybridized carbons. So when you label these, don't just say sp3 and don't just say CH, because I want to know them both. I want to know that you know that they're CH stretches, and I want to know that you know that the carbon is sp3 hybridized if they're less than 3,000 wave numbers. So when I label that, I would label it as it's a carbon that's sp3 hybridized and it's a CH stretch. So that's how I would label it. And then now, what about this one here? So that one is just above 3,000 wave numbers. So what stretch is causing that signal?
I see sp2h.
Yep, exactly right. And if we had a triple bond and we had something a little bit higher at like 3,300 wave numbers, that would have been a C sp2h. But we know we don't have triple bonds, so we wouldn't expect to see that in this case. All right, and so you definitely want to, I definitely ask you to label all these peaks on a test question. But a lot of this isn't new information, right? I knew I had benzene, so having carbon-carbon double bonds isn't really a revelation. And I know I've got benzene, so having the C sp2h stretches is not a surprise. And almost all molecules have sp3 hybridized carbons. So having the sp3 hybridized CH stretch doesn't maybe tell me that much. But definitely the OH in terms of determining the structure, that's a big help. And so now also I've determined my oxygen, right? So I only had the one oxygen, and so I know what the oxygen is now. It's part of the OH. So I know I've got a benzene. I know I've got an oxygen. I know the formula. I'm going to clear these drawings and go down to the proton NMR spectrum. Okay, so for the proton NMR, the first thing I often do is add up my integration values, because if there's any symmetry in the molecule, then I might have multiple hydrogens contributing to the same signal, and uh, and I might get like in the example that we had in the NMR examples that we were just doing, where we could reduce the number of hydrogens to give us the actual integration values. Here we're kind of going in reverse. If I add up my integration values and it's less than the number of hydrogens I have, then that tells me I have a lot of symmetry. But if I add up all of my integration values and it matches the number of hydrogens I have, then I know I've found all my hydrogens. And so that means that the integration values are the actual number of the hydrogens that are contributing to that signal. And so I have 6, 7, 8, 9, 10, 11, 12. And so that matches my number of hydrogens. So I know there's not a huge amount of symmetry in this case. And so after I check that, the next thing I look at is common fragments. In the chat, I can see people have already told me some of them. So, and I'll ask how you know these in a second, but I definitely have a pair of benzene. And I think, depending on how you look at it, there's at least one other common fragment, and the other one you might or might not call a common fragment. So what's the other common fragment that I know I definitely have based on the NMR spectrum?
Propyl.
Isopropyl, exactly right. And what Caitlin was looking at is if I have, so this peak with an integration value of 1 down here, it is a septet. It has 1, 2, 3, 4, 5, 6, 7 peaks. So its multiplicity is 7. It's a septet. And then downfield from that, I have a doublet with an integration of 6. And so these two peaks together, a septet with an integration of 1, and if I also have a doublet with integration of 2, together, this tells me I have an isopropyl. Right, and I also know specifically, right, this one here with an integration of 1 and a septet, that is being caused by that hydrogen in the isopropyl. And the doublet with integration of 6, that's being caused by the 2 methyls of the isopropyl. So not only can I, when I see that pair, not only can I say it's an isopropyl, but I can also say which signal is caused by which specific hydrogens in that isopropyl. And then people are telling me that you have a parabenzene. I'll just say for this one, this is what they were looking at when they told me they have a para-disubstituted benzene. So anytime you see anything between about 6.5 and 8 ppm, right? So anything between 6.5 and 8 on the x-axis, that's going to be a benzene ring. And we know we have a benzene ring, so we expected to see something there. But anytime you have 2 doublets, with both with integration of 2, not only is that benzene, but specifically, that tells us that it's parabenzene. And so I have a benzene ring where I have 2 substituents, and they're coming off opposite carbons. So from the NMR, I don't necessarily know what's on there, but I know they're not hydrogens. I've got 2 things that aren't hydrogens, and they're directly across from one another.
Dr. Shepard, sorry.
Yes, go ahead.
When we have like a septet in one, it could be like a key that we have alcohol, or it's difficult to say look like that. Because
No,
I
so-
remember
Yeah,
that
a septet is not is definitely not going to be an alcohol. If there's also a doublet, then it's an isopropyl. If there's not also the double integration of 6, then it just means there's a group of hydrogens with 6 identical naming hydrogens.
Okay, just because I remember last semester that you told us that we know that we have alcohol when we have like one, and I don't remember if it was septet or single, something like that.
Oh, okay. So yeah, so an alcohol will always be an integration of 1, and it will always be a singlet, not a septet, but a singlet.
Okay, got
Right.
it.
So that actually goes to, so I've identified all the peaks in my NMR spectrum so far except 1, right? And so the one I haven't identified yet is this one. But as Caitlin was just talking about, I know I have an alcohol, and so I would expect to see that in my NMR spectrum, and my alcohol is almost always going to show up as a singlet with an integration of 1. And so the fact that I know I have an alcohol and also that I have a singlet with an iteration of 1, that is my alcohol. So I think I've identified my pieces, right? If I think about my formula, so my formula is C9H12O. So if I think about my carbons, that's going to be benzene is going to give me 6 carbons, and then the isopropyl is going to give me 3 more. So I've accounted for all 9 of my carbons. The alcohol is going to account for the oxygen. And then for the hydrogens, the isopropyl is going to give me 1, 2, 3, 4, 5, 6, 7. The alcohol is going to give me 1 more for 8. And then my benzene ring, since it's di-substituted, it has 1, 2, 3, 4 hydrogens. So 7, 8, 9, 10, 11, 12. So if I have a benzene, an alcohol, and an isopropyl, that accounts for all my atoms. It accounts for the C9H12O. I've accounted for all of my degrees of unsaturation. All 4 are going to be covered by the benzene. So now I know I have all my pieces, and so now I just have to put it together. And so I know I have the pair disubstituted benzene, and it's got to have 2 different things coming off opposite ends. And I know I have 2 other things. I have an isopropyl and I have an alcohol. So in this case, there's only one way that I can think of that I can put these together. And so let me clear my drawings here. And so my molecule, I think the only way that I know to put those 3 together would be to have my benzene and then the 2 other things I have, and they should be on opposite ends of the benzene ring. I have an isopropyl and I have an alcohol. So this would be my prediction for the structure of our molecule. All right, so before we look at the carbon-13 NMR, any questions about my predicted structure? Okay, so now if you noticed, I haven't even considered the carbon-13 NMR information yet. And this is typically how I attack these problems. I find most of the time I can determine what my structure is just based on the mass spec, the elemental analysis, the IR, and the proton NMR. And then what I usually do is I use my carbon-13 NMR as a double check. And so I predict what my carbon-13 NMR spectrum should look like based on my molecule, and then compare that to the actual carbon-13 NMR spectrum. And if my predictions match the actual spectrum, then that makes me feel pretty good that I probably have the right structure. So if I'm looking at this structure, the first thing I would ask is how many signals there would be in the carbon-13 NMR. And so as a reminder, the number of signals in carbon-13 NMR is determined by the number of unique carbon atoms now, not hydrogen atoms, but the number of unique carbons. So how many unique carbons would I have in this structure? Yeah, Kendall, Nahom, absolutely. I would agree. I would count 6. So I'm going to try and circle these again. So my 2 methyls on the isopropyl, that's going to be 1. The CH, this carbon, I'm sorry, I think I said carbons or hydrogens. I misspoke. We're doing carbon-13 NMR. So these hydrogens are identical in the proton NMR, but we're talking about carbon-13 NMR. So it's the carbons I'm thinking about. So these 2 carbons are identical. This carbon is unique. I've got this carbon on a benzene. It's got a substituent on it, but its substituent is an isopropyl, right? This carbon of the benzene also has a substituent, but its substituent is an alcohol. So that means those 2 carbons are not the same. So this carbon would be its unique signal. And then this carbon down here would also be its unique signal. is this carbon unique, or would it be identical to another one?
It will be identical to another one.
Yep, exactly right. So this carbon, it's a benzene carbon. It has one hydrogen, and it's one away from the isopropyl, and it's two away from the alcohol. This carbon also is CH. It's also one away from the isopropyl, and it's also two away from the alcohol. So that means that, change colors. That means that this carbon and this carbon are the same. And so they would contribute to the same signal. And then for the same argument, these two carbons would also be identical. And so that's how we get the 1, 2, 3, 4, 5, 6 signals. All right. Now, if you, again, I'm not going to try and share it, but if you have the data packets that I handed out last semester, and I think Dr. Morton and Dr. Park used the same data packets, so they probably gave those to you as well. Either way, I'll post those online when I'm done doing the examples today. But it has the tables with the chemical shifts in carbon-13 NMR, and so we could use that to help us. But if I consider this the two carbons on the top, the two methyls from the isopropyl, what would their multiplicity be?
Double.
Okay, so I know where you're getting doublet from, and so you want to remember that for carbon-13 NMR, the splitting isn't determined by neighboring hydrogens. In carbon-13 NMR, the splitting is determined by the number of hydrogens on those carbons, but we still add one. So it's not neighboring carbons anymore. It's actually hydrogens on those specific carbons. So then for the red signal, we have, we would consider them separately. This carbon has 3 hydrogens. So 3 plus 1, it would be a quartet. And now, if you have that carbon-13 chemical shift table handy, it might be easier to answer it. But if not, or if you have the table, or if not, either way, do you remember what the chemical shift is going to be if I have carbons that are sp3 hybridized and they're not connected to something electronegative? So they're not connected to oxygens or pi bonds or anything. Where is its chemical shift going to fall roughly?
Wouldn't it be further to the right?
Yes, it would be, and it's going to be between 0 and 50. And so, and you could get that, the number I threw out there, the 0 to 50, you could get that from the table on those charts. And so what I'll do is then look for, do I have a quartet with a chemical shift, a ppm between 0 and 50? And I do, right? And so, well, let's use the same color. Right, this is, if our structure is correct, that's going to be due to the 2 methyls from the isopropyl. Right, so then our pink signal, it has 1 hydrogen, so it should be a doublet. And then again, it's not direct, it's not part of a pi bond, it's not connected to an oxygen, so it would also be between 0 and 50. But it is closer to the benzene, so I'd expect it probably to be higher than the previous one. And sure enough, I've got a doublet at 33. So that's in between 0 and 50. It's a little bit higher than the methyls because it's closer to the benzene ring, but that is almost certainly the CH from the isopropyl. Okay, now tell me about the green and the orange signals. They have each of those carbons has no hydrogens. So what are they going to show up as? In terms of their multiplicity.
Singlets.
Singlets. Yep, I'm seeing that in the chat too. Since the green here and the orange here have no hydrogens, they're going to be singlets. So I would expect to see 2 singlets, and I do. And then the benzene carbons, or any carbons that are part of a double bond, and the benzene carbons are always part of double bonds, they're going to be between 100 and 150 ppm, or they should be. And my two singlets are, like this one is definitely between 100 and 150 ppm. Wait, where did it go? Sorry. This one is definitely between 100 and 150 ppm. And this one's a little bit higher. 153 is not crazy. Plus, that is probably specifically the orange one, because, and the reason it's a little bit higher is because not only is it part of the benzene ring, but it's also directly connected to the OH. Now, sometimes it can be hard to predict which specific singlets are which singlets, but we're probably safe in this case. So that is probably the orange. The 141 singlet is probably the green. And then we have two doublets, and the blue one here and the black one here should be doublets. And it's hard to say which one is which. It can be tempting to say that this is probably the 127, the black one, because it's closer to the alcohol, but sometimes it doesn't come out to be the way we expect with the benzene carbons. So especially for the doublets, I'm not going to say which one is which, but I know one of them is 127 and the other one is 115. So my carbon-13 NMR spectrum exactly matches what I would expect for the carbon-13 NMR spectrum from this molecule. So that gives me extra confidence that I probably have the right structure. All right. So any questions on this example? Okay. So I'm going to go ahead and clear this. And let me stop sharing. All right. And I'll be honest, I'm having flashbacks to the pandemic. I've forgotten how much longer everything takes when we have to do it by Zoom, or at least how much longer it always takes me to do things by Zoom. Okay, so there are if you want more spectroscopy practice, there's a bunch of problems posted on D2L. The ones in the spectroscopy practice, if you had me last semester, unfortunately, those are not new. So finally, good news for those of you that didn't have me, all those spectroscopy problems you might not have seen before. But I'll try to continue to add more spectroscopy problems every week to give you more practice. And as long as you don't, if it's been a while, you probably don't remember the answers just by looking at the spectra. So they may still be good practice. But there is another one. There's a spectroscopy practice 2 in the lab 1 folder that I haven't given before. And so that should be good practice as well. And I'll continue to add more of those every week if you're looking for more spectroscopy practice. All right. So I did want to do a little bit of synthesis practice too. It's this spectroscopy took me a little bit longer than I thought it might. So I don't want to do a whole ton because I don't want to use the whole time. I want you to have time to work on quizzes and things, but let's at least look at a couple synthesis examples together. And so what I'm going to do, the document I'm getting ready to pull up is posted on D2L as well. It's in the lab 1 folder. It's the synthesis practice. Let's see where that is. No, I don't have to pull it up. Right. All right, so I'm going to jump down. I'm going to start with number 3. So And you know what? I'm gonna actually pull up my Word document instead, because that'll be easier for me to annotate, I think. All right. So if I'm given this synthesis problem, I'm said, come up with a synthesis, show me all the reagents and intermediates that there would be. The first thing I would do is say, okay, did my carbon skeleton change? And so when I compare my reactant to my product, it definitely looks like it changed, right? It's not a huge change, but any change is actually huge. And so I have this extra methyl group that I didn't have before. So I definitely made a carbon-carbon bond. And so then I'm immediately going through my reactions and say, okay, to make a carbon-carbon bond, I only know three reactions that can do that. There's the Gilman's reagent, there's terminal alkylation, and there's the new Grignard reagent that we learned. And I'm going to be honest, I hate the Gilman's reagent with a fiery passion. But I know my other colleagues that teach Ergo 2 sometimes give examples that use it. And so I'm always careful to make sure I cover it when I do Ergo 1, because I don't know who my students are going to take in Ergo 2, and I don't want them to be disadvantaged. But I will almost never use it in examples this semester. And that's because it doesn't actually, in practicality, it doesn't actually work very well. It's not a very efficient reaction, and I don't think in practice it's really used all that much. And so it's kind of a cheat code. Like you can, in principle, use it for all kinds of things, just on paper, but it doesn't actually work in practice. And so I will rarely give examples where you have to use the Gilman's reagent. So just a heads up when you're working my problems. If you're finding yourself using the Gilman's reagent a lot, there's probably a better way to do it, or at least there's another way to do it. Okay, so if I rule out Gilman's because I hate it, then I'm also looking for other clues as far as, okay, might I use terminal alkylation or might I use the Grignard reagent? And so for the terminal alkylation, is there any evidence that I might have had a triple bond involved? And for the Grignard reagent, when I see alcohols, that's a good sign. My first guess is I'm going to try to use the Grignard reagent because I know, right, for the Grignard, I either need an aldehyde or a ketone or an ester, but it's going to make an alcohol. So if I have alcohols, or even if I have, when I have, if my starting material has aldehydes or ketones or esters, well, hell, I've already got what I need to use a Grignard reagent, so I probably want to try. But also, if my products have aldehydes or ketones, I think Grignard reagent too, because it's really easy to turn the alcohol into an aldehyde or a ketone. So I guess maybe a simpler way to say it is oxygens. If I see oxygens, my first attempt is going to be to try to do it with the Gilman's reagent. And sorry, I saw some chats come in. Yeah, and so there are a couple ways that we could do it. In this case, I don't think we need to make it a tosylate. So if I assumed I was going to do this with a Grignard reagent, much like last semester, I don't do the formal retrosynthetic analysis, but I think the useful part of retrosynthetic analysis is working synthesis problems backwards, starting with the last step rather than necessarily the first step. And I would probably try to do that here. So I would say, okay, if I was going to do this with a Grignard reagent, So how many carbons do I need to add? What's the length of the carbon chain that I need to add?
One carbon?
Yes. So I want my Grignard reagent probably to have, if I'm going to go that route, to have a methyl group. So the Grignard reagent that I probably want to add is methyl MgBr. And then I need the water workup or the acid workup, the H3O plus, to make it neutral. And then there are a couple right answers. But if I just want to add one R group, what functional group should my starting material have? Yeah, Nahum, exactly right. It needs to have a C double bond O. And so in this case, I want a ketone. Because if I have that ketone, it'll add my methyl from the Grignard reagent to that carbonyl carbon, and it will reduce the ketone in this case to the alcohol. So if I start with this ketone, if I react it with this Grignard reagent and then hit it with H3O plus, that'll turn it into this alcohol. So now my task is to turn my starting material into this ketone. So can we do that in one step? Can I turn a secondary alcohol into a ketone?
Yes, you can.
I can. And I think there are a couple different reagents that I could use to do that. Does somebody want to give me their favorite or one that would work for this? Yeah, no, PCC. Yep. So, and I said favorite. I know you just started. You don't have favorites yet, but you will. By the end of the semester, you're going to have favorite reactions. So I would use, so PCC, and then the dichloromethane is just a solvent, but we often include it in the reagents when we use the PCC. Could we, so that works. And so this would be a good synthesis for this problem. For this step where we use the PCC, could we also have used potassium dichromate and sulfuric acid? Yeah, Colin, we could absolutely. So sodium dichromate is a stronger oxidizing agent than the PCC, but alcohols can't be oxidized past ketones, or I'm sorry, secondary alcohols can't be oxidized past ketones. So if it was a primary alcohol, the sodium dichromate would have taken it to a carboxylic acid. So if I'd had a primary alcohol and I was trying to make an aldehyde, then I would have to have used PCC. But in this case, because it's a secondary alcohol and secondary alcohols can't be oxidized further than a ketone, the PCC would work. That would be perfect. But if you'd used the sodium dichromate, that also would have worked in this case. And you also could have used the greener reagents, the DMP or the Swern oxidation as well. All right. Any questions on this example? Okay, let's do one more, and then I'll let you guys work on uh, whatever it is you want to work on. So let's do. Um, did Grignard? Let's do number 9. Okay, so same question I always ask when I approach a synthesis project or synthesis problem, and that is, did my carbon skeleton change? And this was maybe obvious, but I'll ask it anyway. Did my carbon skeleton change? Yeah,
Yes.
for sure. Yep, I had a 4-carbon chain with a methyl. Now I have a 6-carbon chain with a methyl. So I'm thinking terminal alkylation, Grignard reagent, or if I'm hating myself, the Gilman's reagent. Now, is there any clue in the final product that would make you lean towards one of those three?
The bromines, maybe the alkynes instead.
Yeah, you're absolutely right. So we encountered a reaction last semester. If I have a triple bond and I hit it with excess Br2 or excess Cl2, that'll put 4 of those halogens on the carbons that were part of a triple bond. And so if I see 4 halogens, that's just screaming to me, I have to make an alkyne to do that. And if I'm going to make an alkyne to put all those bromines on, well, let me try using an alkyne to add those extra carbons and using terminal alkylation to extend my carbon chain as well. And so this is another problem where I think it makes sense to start backwards. And that's not always the case. And if you see the path to get from the reactants to the products without working backwards, like you don't have to work backwards. But I think sometimes it does help to do it that way. Because what reaction I start with, maybe that's not obvious, but I know what my last reaction has to be. If I'm going to put those bromines on, then that would have had to have come from one, two, three, four, and I have a methyl on the end. So that had to be my starting alkyne. And I'm sorry, the drawing is even worse than normal. And so if I have that alkyne, what reagents would I use? No, I'm sorry, I'm a moron. That's not right. Let's try that again. How about having the correct number of carbon atoms? So I think that would be the alkyne that we would make. 5, 6. Yeah, that's the alkyne that we would make our thing loaded up with the bromines. So how do I add 4 bromines to an alkyne? Yeah, excess Br2. Okay. And so when I'm thinking how to proceed next, all right, well, I've got to turn that alcohol into an alkyne. That's going to probably take multiple steps. So I'll come back to that. I also need to add an ethyl group to my alkyne because I started with 4 carbons. I got to add 2. And so that might be working backwards what I would fill in next. So I want to add this ethyl group to the end because my starting material has 1, 2, 3, 4 carbons. So to add those 2 on the end, I want to do terminal alkylation. So if at some point I could get to that alkyne, then I'll just go ahead and put in the reagents. This one's hard to put in the chat, but we would use NaNH2, and that's going to pull the hydrogen off the end of the alkyne. And then I want to react that with a primary alkyl halide. Yep. So in this case, since I want to add 2 carbons, ethyl bromide would be the way to go. All right. So then I'm thinking, all right, I've added my carbons, I put on all those bromines. So then continuing to work backwards, I see that triple bond, and we only really know one way to make a triple bond. And that's if I start with an alkyl dihalide. So if I was to start with the only way to make that we know and they could be bromines or chlorines, that doesn't matter. But I would have to have two halogens. And then if I have two halogens and I react it with excess NaH2 and water, that'll give me a double elimination reaction, and it'll convert my alkyl dihalide into the alkyne. Now, these could have been bromines or chlorines. That doesn't matter. I mean, technically, it could have been iodines or probably even fluorines, I guess. And in principle, they could have been, both bromines could have been on the same carbon. But the reason I didn't do that is because the only way we know to put two halogens on the same carbon is if I started with a triple bond. So if I'm trying to make the triple bond, like, I don't want to have to start with it to make this thing because I'd have already had the triple bond that I needed. So when we're doing synthesis, unless my starting material had both halogens on the same carbon, the halogens are probably going to be on opposite carbons if I'm trying to make a triple bond, because otherwise the only way to put two halogens on the same carbon would have been to have a triple bond already in the first place. Hold on. Can we leave out? Yes, right. So Colin, you're absolutely correct. Colin asked if we could have rather than doing what I did in going from here to here into two separate steps, you could combine these two into one. And so if you reacted it with excess NaNH2, that's going to eliminate both bromines, and it's going to give me the triple bond, but it's going to have the negative charge on the end. And so then rather than adding water and then having to add NaNH2 again separately, you could have just done excess NaNH2, and then instead of putting water here, just put the ethyl bromide down, and it would have been perfectly good and arguably even better to go directly from here to here. I just sometimes like to break it out. I think it makes it a little bit easier for some folks to see what's happening. Okay. All right. So now I keep saying this because I want to emphasize that there's not one right strategy to necessarily follow when you're attacking these synthesis problems. We could now start from here and try to make the dibromo thing, but for the argument's sake, I might continue working backwards because I also know there's only one way that I know to put two bromines on adjacent carbons. And that reaction is if I start with an alkene, a double bond, and I react that with Br2, that'll put two bromines in addition reactions onto my pi bond. So that almost certainly has to be the previous step to the one that we've just done. And so now at this point, I probably would start working forward because now and we did a lot of examples of these last semester. I really just need to move that functional group. I need to take off the OH and turn it into a double bond and then move that double bond over. So whenever we need to do that, whenever I'm just moving a functional group, we want to use alternating addition and elimination reactions. And so make a double bond, put something on. Make a double bond, put something on, and keep doing that until we get it where we want it. And the reason the elimination and addition are useful is because for the elimination, I can use bulky bases or normal bases to control where the double bond goes. And then when I have the double bond, I can use HBr or HBr-ROR to control whether I get Markovnikov or anti-Markovnikov addition. And so I can often control where those functional groups end up, and I can move them. So since my starting material has an alcohol, not a double bond, I want to start with elimination. And since I'm trying to get my functional groups over here, I don't want to put my double bond on the methyls. I want to put the double bond here. And so there are a couple ways that we could do this. What's one way that I could take my starting material and make that alkene?
You could change the OH into OTS via tonsilate pyruvate and then T-buc, I think.
Yeah, so that is so turning into a tosylate is definitely one way that that we could do it. And in the chat, Nahom put another way. But right, Colin is correct. We don't want to use the potassium tert-butoxide because that would give us the less substituted alkene. Potassium tert-butoxide would put the double bond here. So the TSCL and pyridine would turn it into a tosylate, and then I just want to use a non-bulky base. So NaOH would be a good choice. And so we could do TSCL. I'm going to do what Ozioma said because I saw that one first. So she said we would do TSCL and pyridine, which turns the OH into a tosylate, and then I can eliminate that with NaOH. And that would work. Nahom's would also work. So we could use HBr to give us a substitution reaction, and that would turn the OH into a Br. And then now Br is a good leaving group, just like a tosylate. And so HBr and NaOH would work. And there's at least a third way that we could do it. What's another reagent that we could do where it would just be one step?
But if we use NaOH, won't it give us like the major product or the more substituted size step product? And this one seems to be on the less substituted part, trying to get a double bond on the less substituted part,
We
right?
will have to move the double bond again after this step.
Oh, I'm sorry. Yeah, I see what you're saying, Nahom. Right. So eventually I want the double bond on the end, but
Oh, yes.
I can't do
Okay.
that
I
in
see
one
it now.
step. Right. I've got to put the double bond here first.
Okay. Yes. I see now.
Yep. I see what you guys are saying. And thanks, Colin. I didn't see how they were thinking. And so I was not going to answer their question helpfully. And so that helped me. Thank you. Right. And so to answer my previous question, we also could, oh yeah, Colin's got it. Concentrated sulfuric acid. So if I have an alcohol and I hit it with concentrated sulfuric acid, that will give me elimination. The downside of that is it will only give me the more substituted alkene, but in this case, I want the more substituted alkene. So concentrated sulfuric acid would also have worked. All right, and so now that I've done the elimination, I want to do addition. And so I want to use either HBr or HBr-ROR, and I want to pick the one that puts the double bond, or not the double bond, but puts the bromine in the direction I want to go. So I'm going to kind of do a zigzag because I'm running out of room. But if I wanted to put the bromine there, would I use HBr or HBr-ROR?
HBr roar.
Yep, because this carbon is more substituted. If I just use HBr, it'll put the bromine there. Since I want the bromine on the less substituted position, that would be HBr-ROR. All right, and then now the last step, and so now I do want the less substituted alkene, right? So if I used NaOH again, I'll go backwards. I put the double bond here. If I want the less substituted alkene, which I do, then I want to use a bulky base. And so now we would use the potassium tert-butoxide. All right, and so I know this is longer than some of the ones we maybe did in Orgo 1, although sometimes I'll sneak in a long one every now and then. But it's good practice for this semester because we're going to want to work to build up to these longer syntheses. But I think with these longer ones, it also strongly makes the case for sort of practicing working backwards because like trying to do this all in your head and picturing every step that we're going to need to take to get from here to here and do all 6 or 7 steps, depending on how you break them up. And keeping track of all that at once is kind of hard. But by working backwards, like at least this last step and the second to the last step and this one, they're kind of unambiguous. There was really only one way that we could have made each of those subsequent molecules. And so that's how working backwards can often help us. And then once I get to the point where I can kind of see how to connect my starting material with where I ended up, then you can kind of start working forward. Or sometimes I go forward and back until I kind of meet up in the middle. All right, so I am going to stop sharing and stop recording.